You have used Python lists all term. You have indexed into them, sorted them, appended to them. Yet you have never once needed to know how a list is arranged in your computer's memory. Somebody made that decision behind the scenes, and it never mattered to you. That is data abstraction working exactly as intended. In this video, we practice it on 5 designs: the list itself, an elevator, an employee, a queue at a store, and a stack of pancakes. By the end, one idea will stand out. Behavior, not internal representation, is what defines a type. Start with an example closer to home, the list. Somebody behind the scenes wrote the code that defines the data type list, the data that makes up a list, and the behaviors a list can perform. On the data side, whoever created the list class faced a genuine choice. One option, allocate one contiguous block of memory and place the elements in that block in order, from the smallest memory address to the biggest. Another option, allocate memory here and there, wherever space happens to be available, and represent each element by 2 things: the value stored at that location, and the number telling Python which memory location holds the next element. Both are valid design decisions. Either layout gives you a perfectly working list. On the behavior side, you already know a lot of what lists can do because you have been using them all along. You can index into a list, you can sort a list, you can append an item to the end, you can ask for the maximum element. Every one of those operations has worked for you all term. And not once did you need to know which layout the designer picked. The internal representation stayed hidden while the behaviors did the work. That separation is the whole point of the abstraction. You program against what a list does, not against how it is stored. Now practice the same 2 decisions on everyday things. An elevator, at heart, is a box that can change floors. For its data, one reasonable representation, a length, a width, and a height, all floats, plus a maximum capacity and the current floor it is on. Those 5 values together represent the elevator, again a design decision, and yours might be different. For its behaviors, the elevator can change its current floor, which really means changing the value of the variable that holds it. It can add people perhaps checking against the capacity limit and printing a warning if you go above it, and it can remove people. An employee is one of the most common examples. It gets implemented in a lot of programming languages. An employee is a person who has a salary and works for some company. One representation, a string for the first name, a string for the last name, a birth date, and the salary as a float. And the behaviors change their name, change their salary, and activate or deactivate them as a current employee. Data plus behaviors, chosen by the designer, the same pattern again. A queue at a store goes hand in hand with a stack of pancakes. So take the queue first. Its representation can be something really simple. Just a list, holding strings with the names of the people currently in line. Nothing about that list is special. What makes a queue is not the representation, it is the way you use it. In a queue, the first person in is the first person out. So if your design decision is to add new arrivals at the end of the list, then when you remove someone, it had better be the oldest person at the beginning of the list. Use the list consistently that way, and you have simulated a queue. A stack of pancakes is very similar, with one twist. The first pancake you make is the last one you eat. First in, last out. The data representation is identical to the queues. A stack of pancakes is also just a list. Only the behavior differs. A newly made pancake goes on the end of the list, and when you take one to eat, it also comes off the end of the list. Same representation, opposite rule. And the difference alone is what makes one of these a queue and the other a stack. Here is the big idea, and it trips up many people meeting object-oriented programming for the first time. You're in charge of the design decision. You decide what data represents the class, and you decide what behaviors it has. Represent the queue as a list where new items get added at the end, and to be a queue, you must remove from the beginning. An equally good design adds new items at the front, and then, to stay first in, first out, you remove items from the back. Either way, the behavior is identical. Both designs implement a queue. The reason for all of this, object-oriented programming bundles data and behaviors together into one package that lets us create many objects of the same type that all function the same way, consistent in the data that represents them, and consistent in the way we use them. We know for certain that our queue behaves first in, first out. In Python, the bundling mechanism is the class, and we write classes to make code that is nicely reusable. Write a simple class once, then build on it to create more complex classes, and keep the deeper lesson from the queue and the pancake stack. Their representations were identical. What defined each type was the behavior we guaranteed. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.